Now, welcome back from the break, and we will proceed with more fantastic statistics. And what we can also do, like we saw last time, we had a single or one sample, and then we could look at the confidence interval, and we could actually know which null hypothesis we would reject. The same, we can do the same for the interval, confidence interval for the difference. We can calculate that, and it is simply done by, here it's a y, should be x1 and x2, I think. But the confidence interval is simply calculated by taking, it should be x1 bar x2. It's calculated by taking the sample mean, so the average of each sample, and the difference, and then plus minus in the same t-distribution times the square root of the sample deviation from one sample and the number of observations from that sample and the sample deviation from the other sample divided by the number of observations from that sample. So, and there was also a question why sometimes it's capital letters, sometimes it's small letters. Capital letters would be when we write it up with stochastic variables, so that's before you do the experiment and you want to calculate on these things and the probabilities and such things. Once you have observed the values, so here you write it with small letters, and that means now we have observed the two sample means. Yeah, then it's the sample means, and the plus minus is so. That gives you your confidence interval like this, which should read. I mean, I got these from Peder. It should read x1 minus x2. So around there, around the observed difference, we should have x1 minus x2 plus this from the quantile, 97.5 quantile in the t-distribution, but scaled up to the x, or to the you could say the units that we measured this in. So megajoules for the example with the nutrition, and down here minus this quantile because the t-distribution is symmetric. So the point is that 95% of the time, for the confidence interval, if we repeated this experiment and observing this data again, we would 95% of the time, if alpha is 95, we would have the real difference would be within this interval. So there's a real difference between the mean values at hospital B and at hospital A and hospital B. There's a real difference, and if we go and observe, we observe these 9, let's say in each of these samples, and we calculate actually. Now it should read the difference between those two sample means. So we calculate from these 9 observations the mean, the average, that difference, and then we add this to get to the upper limit of the interval and subtract it over here to get to the lower limit. Then in this interval, if we repeated this experiment and calculate this again, 95% of the time, if we had alpha equal 5, 95% of the time, the real difference would be inside this interval. Sometimes it would be out here, but 95% of the time, when we repeated the experiment and calculated this, the real one would be inside this. And what we also know then is that if we would state a null hypothesis that the difference was was out here, then we would, by calculating the confidence interval, we could say that we would reject this null hypothesis. So if we calculate this confidence interval, and the null hypothesis often is there a difference, or the difference is equal to 0. So if 0 was outside this confidence interval, then we would know that we have found a significant difference in this particular case that we had that. And we call these values, in the t distribution, we call them the critical levels. So, So for the example with the nutrition, we would calculate the difference here. Okay, first we would get the quantile, 97.5 quantile in the t distribution. So we would take the t distribution with these number degrees of freedom, and we would go in and say where is the value? I mean, on the x-axis, which value? Where is the value where we have 95% of the probability mass below? We go in and take this value. That's 2.12, and then we simply calculate the average of the one minus the average of the other, plus minus this quantile, times the square root of, we calculate the sample standard deviation of the one divided by 9 observations, and the sample standard deviation of the other divided by 9 observations. So then we have the confidence interval, and that gives the result that we have a 95% confidence interval, that the difference, the real difference in mean is between 0.95 and 3.42. And then we can already see that if we should ask the null hypothesis, there is no difference. That means that mu A and mu B minus each other is equal to 0. Then that 0 is not included in this confidence interval. Therefore, we know that we would reject this null hypothesis, which was also the case that we did that when we did it the other way of calculating or the standard way of calculating the hypothesis. So in R, we can do these things, and we can simply write in the values that we have. Usually we would of course have a usually we would have the values from some data file. I mean, maybe statistics these days it could be that you have millions of observations, and then we of course don't write all the values in R. We would have them in a file, so we'll read it as you do in the projects. But here I can just define two vectors. Now I ran this line, so if now XA is these 9 numbers, and I can set XB, so that's the numbers from the example, and then I can simply write, last time we used t-test and we only wrote one of them, but if I write both of them, give them as argument to the function t-test, then I simply get this result of the Welch 2-sample t-test, and I can see that I get the same p-value that I got, and also this confidence interval that I calculated is the same. So the point is, you don't need to write these long formulas for the degrees of freedom and all of this. It's implemented in R. If you wanted to take out the confidence interval from this function, then the point is that if you run, let's just run this one, t-test XA. If I wanted to take out the confidence interval of this one, I could write, now it's more like an R thing. If I keep the result of t-test, that's returned into a variable called val now. So I can actually write class val. So then I can see the class of val, and it's called h-test. So it's just something that t-test return. But the point, if I write val and then a dollar sign, and then I press tab, then I can see what is returned by the function t-test. So it returns, it's a list of all these things. So if I wanted to take out the p-value for some later calculations, I could write it like this: val $p-value, and then I would simply have this value. Or if I wanted the confidence interval, I could find that here, confidence interval. So it returns the confidence interval, and then I can also see it also returns the confidence level, which I could of course set different when I ran t-test function. And if I wanted to take the lower limit, I could just write 1 here, take the first element, that's the lower limit, and the upper limit would be the second element. So it's just if you wanted to use this for in some other calculations, you could take them out like that. Maybe in the projects you need to do that. Okay. Then the next